Lesson 30 on linear regression. Here we go. So if you have not had a chance to check out the linear algebra review and you need one, please go back and check that one out first. But I'm just going to go ahead and assume that everyone, at least that needed it, went and checked that sucker out first. Okay, so let's introduce, like I told the folks that have reviewed it, that I'm going to start off with just introducing the linear regression problem, or the least squares problem. So introducing the least squares regression problem as an example. So we're just going to give an example as an example. Understanding that this example is not it doesn't matter how many points you get. Doing this process will get you the same answer regardless of whether there's an example or not. But I think it's important to sort of see an example first. So I'm going to give you 3 points, 1, 3, 2, 11, and 3, 7. And this is going to be t. This is going to be our y value. And we'll let this be t1 and y1. Let this be t2 and y2. And let this be t3 and y3. So those are our 3 points, and what we want to do is find a line that goes through all 3 of those points. And so that's the idea behind, let's do, I believe I've done this earlier today, that I can make a nicer one using this. All right, good. So let's go back, and I'm going to spread it out a little bit on the t-axis. So this is my t-axis, and this is my y-axis. I'm going to spread it out a little bit. So 1, 2, and 3, and then I got to kind of squeeze it in because I don't have I got 11 that I need to get up to. So it's maybe 1, 2, 4, 5, 6, 7, 8, 9, 10, 11. Looks like I did an okay job of doing that. And then we'll put in 1, 3, so it looks like it's about right there. We'll put in 2, 11, 2, and 11, which looks like it's about right there. And then 3, 7, so 3, 4, 5, 6, 7, and it looks like it's about right there. And so even without the squeezing of the parameter, I mean, we can tell that maybe we got this line that doesn't necessarily go through all 3 of these points. And so we know that there is no solution to this, right? So if I'm looking for y is equal to c plus d times t, we know right away there is no c and d that solve this, right? So there is no c and d that will work for these 3 points, because the 3 points aren't on the same line. They're not on the same line. Not on the same line. Okay. So we want to find the C and D values. So we want to find the best C and D value. Now, how do I define the best? That's really the question. And here, let's put some points that actually do lie on the line. So if I had, instead of 1, 3, we had 1 and whatever that sucker is, and then 2 and whatever that sucker is, and then 3 and whatever that one is, then we would have a C and a D that would fit it, right? But we don't, so we know that there's going to be a certain amount, regardless of the C and D that we choose, there's going to be a little bit of error involved in these new points. So this should be horizontal. This error is just whatever our difference in the point that's on the line versus the point that we were given. And so we'll let this be our E1, we'll let this be E2, and we'll let this guy be 3, right? So there's 3 of these errors. And the idea behind a least squares regression is what we're going to end up doing is subtracting the value for 3 in this case. For the first one, it'd be 3 minus whatever number that is that actually appears on the line, and that would be a number. And what ends up happening is if you added E1, E2, and E3 together, and then if you just did those by themselves, it would end up being 0. So what we want to do is square each one of those so that we can minimize those. All right. So when we find the best, we want to find the best that minimize the red distances. Okay. So that's how we define the best. In other words, the closest that we can possibly get vertically to those 3 particular points. Okay. So it's called, so this is called least squares because we end up squaring. So E1 squared plus E2 squared plus E3 squared. So we end up squaring that total error. Or sum of squared errors is what here. Matter of fact, I'm going to put that on there. So that might be a term that you might have heard before. So sum of squared error. So we might want to minimize that sum of squared error. So you're looking for the C and the D that do that. All right, these blue points are just points that lie on the line for a predictor. So the blue points are points that lie on the line for a particular C and D. So once you give me C and D, we'll put in 1 into the CD, and then we'll get our point that sits on the line, and then we'll put in 2, and we'll get the point. Let me see. Let me move this over. So I'll put in the point 2, and then I'll get the point here that lies on that line, and I'll put in T equals 3, and then I'll get in the point that lies there. So that's the idea. So we want to find something that lies on the line, and that something that lies on the line corresponds to something over here when we get to our linear algebra version. Okay, so what I want to do next is I just take this idea, or what we just done, and we want to turn it into a linear algebra problem. So turn this into a linear algebra problem, and then we'll draw it and sort of see the different way of looking at it. The linear algebra problem. Okay, so but once we draw it, we're going to come back to this version and sort of tie up all the loose ends here. So how are we going to turn this into a linear algebra problem? I know I want y is equal to c plus d times t. I know I have 1, 3, 2, 11, and 3, 7 are my 3 points. So y1 is 3 is equal to c plus d times 1. All right, I'm getting that from this point. So I'm just taking this point, putting it into my equation, and out comes this equation. This is equation 1. This is from the first point. The second point is the same thing. You put 11 in, is what I want to come out of my equation for a line, and then c plus d times 2. And then 3 is 7 is equal to c plus d times 3. And so this is our, if you remember back, if you go back to the linear algebra real quick review, this was a system of linear equations. So I want to take the system of linear equations and turn it into a matrix multiplication. And so I'm going to take this and turn it into this simple matrix multiplication of 1, 1, 1, 1, 2, 3. And then we're looking for C and D, and then 3, 11, and 7. So I just turn this thing around. I have to put my right-hand side where it's supposed to be. This would be my matrix A. This would be X, and this would be B. And then this is going to give us no solution. So the answer to this question, if you're looking for an x, so there is no solution to this equation. And again, in the linear algebra review, we talked about you could have one solution, no solution, or an infinite number of solutions. And in this particular case, we're looking for one that has no solution. So what I want to do now is I want to take this idea or this equation, this matrix multiplication here, and I'm going to visualize what's really going on here. So what we're going to do is use the columns of A as our two vectors. I'm trying to get this in the perfect spot, but it's just not working for me. Let's see if I can. Yeah, I can move this a little easier this way. So I want to take this matrix A, and I want to use those two vectors that are in the columns. So in other words, I'm going to use 1, 1, 1 and 1, 2, 3 to sort of map out a plane in R3 that we could get to. So all of the linear combinations, and I probably need a different color, so I'll use purple. It didn't look very purple to me. So there we go. So that is a vector that's and we'll call this guy 1, 1, 1. And then I got another vector that's pointing in this direction. That is a different direction than 1, 1, 1, because we know 1, 2, 3 is not collinear with 1, 1, 1. So those point in different directions. And these two vectors make up this plane in R3. So all the linear combinations of 1, 1, 1 and 1, 2, 3 will get to any other place on this plane in R3. Okay, so but the problem is there is no linear combination that'll get to the vector B. And the vector B is this 3, 11, 7. And that's why we don't have a solution. That's why there is no solution to this thing. I mean, if I gave you a B vector that was in what's called the column space, in other words, another vector that lies in the plane, then we wouldn't have any problems, right? There'd be one solution and that'd be the answer. But the problem is there's no solution. So this vector B, is outside of the plane that makes up all of the actual answers that can be solved. So basically what I'm saying is, if you come back here to this problem, it would be all of the answers that lie on this line. So anything that lied on that line would be vectors that lied in this plane. So what we want to do then is we want to find the best one, so the vector that is the closest to this B vector, but it still lies in this plane, because I want to be able to make up linear combinations of 1, 1, 1 and 1, 2, 3 in order to get to that sucker. So what happens, and I'm going to put it in red, is I want to come straight down from the B vector, and I want to end up in the plane. So we're going to, hopefully I can draw a decent, relatively straight. This is also going to be a vector here. So this B vector, I'm going to call it P. This P vector is what's called a projection, and it is the vector that is the closest to the B vector that lies in the plane, and it is right underneath the B, and it's called a projection. So P is a projection of the vector B onto what's called the column space. Now, you don't really need to understand all of the ideas of the column space. Just know that the column space is all of the linear combinations, and I know we talked about it in our review, all of the linear combinations of the column vectors of A. So again, the two column vectors in A were 1, 1, 1 and 1, 2, 3, and that's why I drew them down here in purple. And I can definitely get to that particular point. There's some linear combination of 1, 1, 1 and 1, 2, 3 that will get us right underneath, so that this, and it's going to be an error vector. It's the amount of error that's in our solution here, but so that that error vector is orthogonal to that column space. Okay, so what is P? Well, P is just equal to A times X hat. Now, what do I mean by that? So that just means this X hat is not really C and D, but it's some linear combination of 1, 1, 1 and 1, 2, 3 that gets us to that spot that's right underneath our B vector. So in X hat is the linear combination that gets a vector P that lies right underneath B. In other words, that E, so if I put it anywhere else, right, so I'm not going to keep this vector on here, but if I put this vector P anywhere else, then the vector E would be much larger than the one that I currently have, because it would be way over here. And this one, right, because it would be way over here, and this length of this vector E, this error, if you will, would be much larger than it is currently right underneath. There is no place that I could get that where this error is going to be smaller than where it's currently at when P is right underneath B. So that's why that we use the projection. And hopefully, yes, all right. I was able to erase all that stuff. So if you just imagine putting that P vector anywhere else. And what would happen with your E vector is, because it's not orthogonal, it's not right underneath, it would end up getting larger and larger and larger. So if you put it way over here, then obviously that would be much larger than the current E, and so on and so forth. So we're trying to find this P vector so that this error vector is as small as possible. Okay, but what is P equal to? So if I wanted to, so again, we already have it written over there, but I need to put it over here. So this P vector is equal to A X hat. And it's not A X because we said X was CD. And we know there's no solution to CD, so we're getting the best CD that we can get. So it's equal to X hat. We don't know what X hat is right currently, so I don't know what it is, but we're looking for it. So we are looking for this linear combination. So we're looking for this later, after we do a little bit more. All right, so let's turn to our vector E. So what is E? So E is the error vector. And E is going to be orthogonal to P. And from your linear algebra review, we know that if E and P are orthogonal to each other, then that means that P transpose, so it doesn't matter which one we do, P transpose E is equal to 0. So we do know that. So let's figure out how we can write E. So what's another way of writing E? So your E vector is equal to, well, let's don't do that. Let's remember I mean, that's technically what we're looking for is what E is, but let's remember what is P plus E, right? So go back to the when you add in tip to tail. So I have this P vector here and I have E vector here. So P plus E must equal B. So if you do the tip to tail business, you'll remember that P plus E equals B. And then there was this other, again, E is what we're really looking for. So I know that E is equal to B minus P, which is equal to, there's one more sort of step here, B minus, so what did we say P was? P is equal to AX hat, so it's just equal to AX hat. All right, so I'll just give you a second to check that out. So all of this is just algebra that we're doing in this particular piece. Is we're starting here and we're just subtracting P from both sides to get here, and then to go from the E vector is going to be B minus AX hat because P is equal to AX hat. So all of those things sort of come around, and we can say, well, you know what, if this is true, then all I'm going to do is take this E vector and put it in for E. And I'm going to replace that P hat, or that P transpose. So I know that it's going to be A, so I'm putting this in here as well. So I'm putting all of these things sort of all at the same time. And so we know AX hat transpose B minus AX hat. So if we multiply those two, we better get 0. So if we get 0 there, then we know that this thing, which was P, is orthogonal to this thing, which was E. And so remember the transpose rule. So AX hat transpose A transpose times B minus AX hat is equal to 0. And all I'm going to do is, so I'm going to leave X hat transpose out, and I'm going to set that, so times A transpose B minus A transpose A X hat is equal to 0. And now if X hat transpose is not equal to the 0 vector, then what can we say? Then we can say A transpose B minus A transpose A X hat is equal to 0. And we know that's not equal to the 0 vector because that wouldn't make any sense, right? Because that would be this thing that we're looking for, and we don't want that equal to 0. So this is true, and therefore we can take it to the other side. So we know really what we're looking for is A transpose A. So I'm just using algebra now. X hat is equal to A transpose B. So this is the key equation that we're looking for. All right, so again, starting from, and this is true regardless of, I mean, you do recognize that I didn't use any of the numbers in this particular case. I just went into the ideas. Starting right here, we really didn't, I mean, I'm just using the numbers here to draw this picture out, but it really doesn't matter. All of this theory, all these ideas fit regardless of what the number of dimensions for your column vectors, the number of dimensions for your B. I mean, these ideas still fit. So now what I'm going to do is I'm going to substitute our equations or our numbers back in to see what we can get. So I'm going to use this equation here to find X hat. Now remember what X hat is. X hat is the best C and D, right? We can call it C hat, D hat if you want to, but it's the best C and D that minimize the length of our error vector. And why are we care about the length of the error vector? I just want to get back to that here real quick before we go. So in this case, it would be E1 squared. So it'd be the square root of the E1 squared, E2 squared plus E3 squared, which if we minimize this, it's the same thing as minimizing E1 squared plus E2 squared plus E3 squared with respect to C and D. So if I'm minimizing this thing with respect to C and D, then I'm also minimizing this thing with respect to C and D, which is minimize the sum of squared errors with respect to C and D. So it's the same idea. Okay, so again, we're using this guy, and we're going to substitute back in and then take it back to the original problem. So so remember what A is. So A was 1, 1, 1, 1, 2, 3. B was the vector. Let me move up so I can remember it. 3, 11, 7. So 3, 11, 7. So we need A transpose A. So this first, so remember what we're doing here. A transpose A, X hat, that's what we're looking for. We don't know that. And then I'm doing A transpose B. So we're gonna do elimination. We're gonna do this all by hand. Hopefully I made this thing easy enough for us to do it. So A transpose A would be 1, 1, 1, 1, 2, 3, and then 1, 1, 1, 1, 2, 3. So A transpose A is simply equal to, what is that? 1, 2, 3, 1 and 2, 6, I believe. That's another 6, and then 2 and 3 and 9, 4. 9 is that 14? I believe that's 14. So 3, 6, 14. So we have the matrix that goes right here is just this 2 by 2 over here, 3, 6, 6, 14. And now I need A transpose B. So A transpose B is simply 1, 1, 1, 1, 2, 3, and then B is 3, 11, and 7, which should be 3 and 11 is 14, and that should be 21. That's an easy one. And then 3 and 22 is 25, plus 21, 21 and 25 is 46, I believe. Hopefully these come out to the right answer, because I think it made it so that we can solve this relatively easy. And so remember, the thing that we're trying to solve, here, let me put this, so this guy right here turns into, by these two calculations, 3, 6, 6, 14. C and D, we'll call them hats. Hat is equal to 2146. So let's take this downstairs, or down a little way so I get some room to work. And let me put it back up so I can see what it is again. So we got the equation. So here's what we're solving for. So it's 3, 6, 6, 14, 21, 46. All right, so use a little bit of linear algebra, so or a little row reduction, I should say. Pretty straightforward. 3, 6, 21, and then what is that? 0, 2, negative 42. Is that 4? Okay, so now I can use back substitution. So I know, is that C or D? D hat must be equal to 2. And if D hat's equal to 2, that means 3 C hat is equal to 21 minus 12, which is 9. So C hat must be equal, oh yeah, we made it easy. So C hat's equal to 3, D hat's equal to 2. Now this rarely solves like this. I must have done a little bit of work in order to make this thing solve out pretty easily. So what does that mean about our equation? So that we know y is equal to c plus, so 3 plus 2t. 3 plus 2t. So from above, it was c plus dt, and 3 plus, so c hat is 3. So y was equal to c hat plus d hat t. Okay. So we can take this thing, so if we want to, we can just go back up here to the top and write in our solution, or our numbers, right? So I can tell you what, because I know C and D now, I can write in what the blue numbers are. Yeah, let's do it. Let's do that, and then we'll come back down and see what it looks like in the linear algebra world. So we know y is equal to, I probably need to write this down, 3 plus 2t. 3 plus 2t. All right, so if t is equal to 1, 2, 3, if t is equal to 1, this is the, let me put this in a different color. So I'm going to put the actual points in white to 11, so I don't forget what they are, that they're the actual points. And I'm going to put the blue points, the ones that actually lie on this line, I'm going to put those in blue. So at 1, obviously this would be 1 comma 2, 5. And this would be 2 comma 4 and 3 is 7. And this would be 3, 6, 7, 8, 9. 3, 9. Okay. Now, so we know that, let's see, let's call this P1 is equal to 5, P2 is equal to 2, not 2, 7. P2 is equal to 7. And then P3, so this is like our projection that we talked about, right? So if we could come up with a linear combination, in this case it was 3 and 2, that would that we could use our column vectors, right? This was that projection that we talked about, and that's why I'm using these P numbers, and this is supposed to be 9. So now I can calculate my errors, and so my error here would be 3, so we're doing 3 minus 5, which would be -2, 11 minus 7, which would be 4, and then 7 minus 9, which would be -2. And so now we have all of our numbers up here. And so let's just write what P is equal to, and then we'll do it with linear algebra. So it was 5, 7, 9, so 5, 7, and 9. And then E, I guess I should do that in red. Then the red E was -2, 4, and -2. And if you summed these, it would go to 0, right? So that's why we do the squared of each one of these. Now let's see what that looks like below. So we know x hat. Okay, so once we know x hat, so x hat equals 3, 2. All right, so I know x hat is 3, 2. So I know P. So how would I get the P value? Or here, let me get, not the P value. I hate to use that. So how to get the P vector? It was just equal to AX hat. And then what was AX hat? Let's just use A, which was 1, 1, 1. So 1, 1, 1, 1, 2, 3 times 3, 2 would equal, let's see, 3, 4, 5. So there'd be a 5. 3 plus 4 is 7, and 3 plus 6 is 9. Okay, and then error, I put it in red, and then our error vector was equal to, so go back up, it was B minus P. So our error vector is B minus P. In this case, my B vector was, let's see, 3, 11, 7. 3, 11, and 7. And we subtract our P vector, which we got from right here, would be 5, 7, and 9, which would equal to -2, 4, -2. All right. So that's all I got for this one. Hopefully you see why we did what we did for our previous. So I don't know if you remember, but there was a, so like last class we had AX was equal to some B, and there was no solution to it. And so what did I do in R? In R, we used the solve command. And so we said solve matter of fact, let me just use all R commands. So I used the transpose of A, vector multiply I'm sorry, matrix multiply times A, and then the transpose of A matrix multiply times B. Right, and what this does is exactly what we've been doing here. So A transpose A, it finds this X hat that solves this problem here. So this solve command solves that particular problem. So it finds the best one, and it just so happens that the best one is the one that satisfies all of the equations that we had in there. And so that's why this A transpose, I told you guys that we'd come back to this, and while we were doing this business here for each one of them, for both sides, it was because there was no solution beforehand, but when we multiplied by our transpose of A on both sides, then we get a solution. But you get the best solution, and it just happens that it is the solution that satisfies all of our equations, which is what we were looking for. Okay, that's all I got for this class. Hopefully you got something out of it and are able to do any size matrix or any number of points in order to find the least square solutions to our linear regression problem.